Welcome back. AERO4540, Chapter 2. Okay, Chapter 2 is all about the torque-free attitude motion, or the objective of this chapter is going to be to investigate the natural attitude motion of a rigid body. Natural in the sense that we're not going to consider any external torques being applied to our spacecraft, such that we can obtain analytical expressions that would allow us to calculate the components of the angular velocity vector in the body fixed reference frame. These are omega x, omega y, omega z as a function of time. And then the same for the orbital, or not the orbital, but the h, the angular momentum vector. Sorry, thank you. As a function of time, so that would be hx, hy, and hz. So the first thing, again, is to assume that there is no external torque being applied to the spacecraft, and also that we are considering an axisymmetric rigid body. Axisymmetric rigid body means that we're going to consider two of the three principal moments of inertia to be exactly equal, and this is also a key consideration to be able to derive analytical expressions for the omega components and the h components, both in the body fixed reference frame. So you may say, well, if there's no external torque, then that won't generate any rotational motion, isn't it? Well, the answer is that no, because we will nevertheless consider initial conditions on our angular velocity vector and on our angular momentum vector. So the x, y, z components of both vectors at t equals 0 would be considered to be different than 0. Such that we're considering a spacecraft which is already moving in three-dimensional space in terms of rotational motion, yet we're just looking at this natural motion and see how, or analyze how would the angular velocity vector and the angular momentum vector will evolve over time. Okay, so that's going to be the objective of Chapter 2. So torque-free attitude motion. Now, obviously, this torque-free or this natural motion assumption is not true in practice, because a spacecraft orbiting about the Earth or any primary body in space would be experiencing some perturbing torques from the atmospheric drag, from the solar radiation pressure, from the gravity gradient effect, and all those things would torque the spacecraft about its center of mass in some ways. But nevertheless, those perturbations in space are rather small, and if we look at the attitude motion over a short period of time, then the torque-free assumption, it would be kind of valid within that small time frame, okay? So the first thing we're going to do to obtain, at the end of the day, analytical solutions for omega x, function of time, omega y, function of time, and omega z, or in other words, the x, y, z components of the angular velocity vector omega of our body fixed reference frame expressed in the body fixed reference frame, right? So we are seeking analytical expressions for those three quantities. And same for the angular momentum vector components, hx, hy, and hz as explicit function of time. Okay. And those correspond to the x, y, z components of this vector, angular momentum vector, expressed in the body fixed reference frame. And the reason why we are seeking those expressions is that based on that, we will be, or we should be able at the end of the day, because it's kind of complex, but the objective is to be able to figure out what would the motion of these two vectors be in three-dimensional space as time goes by if we don't torque the spacecraft, so it's hands off. And then we're going to relate that to the motion of the rigid body in space as seen from an inertial perspective and try to picture the three-dimensional rotational motion of our spacecraft. And that will be kind of the ultimate objective of Chapter 2. Okay, but in order to do that, we need to obtain those analytical expressions for these two specific vectors from which we're going to discuss about the practical implications in terms of rotational motion. Okay? First thing to do towards this objective is to revisit our Euler's equation of motion. Specifically for the case where we are dealing with an axisymmetric rigid body that would be symmetric about two axes. Okay? So if this is, say, the x unit vector of the body fixed reference frame, the y unit vector, obviously centered at the center of mass of the spacecraft. And we're going to set the z direction of body fixed reference frame towards this axis of symmetry, okay, such that we end up with the principal moments of inertia about bx and about by to be exactly equal to each other, and that one to be different, okay, just because of the sheer geometry of the rigid body considered here. Now, this is obviously assuming a mass distribution which is constant throughout the body, okay? And here, I'm going to say that Jx is going to be equal to Jy by virtue of aligning Bx and By in those two specific directions, and by virtue of the geometry of the rigid body, such that those are going to be referred to the transverse principal moment of inertia, and that will ease up the derivation procedure because those two will be replaced by the same scalar quantity, which is going to be denoted by Jt, T for transverse, and for the Z, principal moment of inertia, so the mass distribution about Bz, we're going to refer to it as the actual principal moment of inertia, and denoted by Ja. And that was transverse. Okay? So based on that, we're going to go back to the simplest form of our Euler's equations of motion, and these had been obtained at the very end of chapter 1 by considering a principal axis reference frame. So we're going to go back to the three scalars equation and replace Jx and Jy by Jt, and then we're going to replace Jz with Ja. And furthermore, we're going to say, well, we are within the torque-free attitude motion. So the second assumption here is that the net external torque applied to our spacecraft, which was our tau x, tau y, and tau z, are all going to be equal to 0. Okay? So let's go back to our previously obtained equations of motion using Euler's equation. And let's make those modifications to the dynamical equations and see what we obtain. So if you were to take the last three equations we saw in chapter 1, we're going to end up with Jt omega x dot plus Ja minus Jt that multiplies omega y omega z. And on the other side, there's no torque being applied, so we're going to set this term to be equal to 0. And then for the y equation, we're going to get Jt omega y dot. Previously, we had Jy omega y dot, but now, because of the axisymmetric assumption, the Jx and Jy are set to be equal and equal to Jt, okay? Plus Jt minus the actual principal moment of inertia, omega x, omega z, also equal to 0. And finally, for z, we're going to end up with simply the actual principal moment of inertia times omega z dot equal to 0. And obviously, because we're starting from these three equations obtained from what we did at the end of chapter 1, it implies that our body fixed reference frame was selected to be a principal axis reference frame, such that we are able to only keep the three principal moments of inertia within the inertia matrix, and set to 0 the products of inertia. Okay? But again, if we look at that from that point of view, you might be tempted to say, well, there's no torque, so then there won't be any acceleration, right? Or think about F equal ma. If you're not applying a force on the object, there won't be an acceleration, and therefore there won't be any motion. Well, no, because then if we don't have external torques, we could pretend that we have some initial conditions or initial velocity components in terms of omega at t equals 0, okay? And this is exactly what we're going to do. So we're going to pretend that omega x at t equals 0, denoted by omega x naught and omega y naught and omega z naught at t equals 0 are not equal to 0. So we are starting the observation of a rigid body in space when that rigid body was already in motion, okay? Yet we're not torquing it, and we're just letting the spacecraft do its own thing under the influence of no torque, and then analyze how would the angular velocity vector rotate in 3D space, and how would the angular momentum vector spin as well, okay? So these are equivalent to omega x evaluated at t equals 0. This is going to be the same as omega y at t equals 0 and omega z at t equal 0, okay? So what will be the motion when this holds true and that they are different than 0, when the rigid body is an axisymmetric body, and when there's no torque applied to it? What would the motion look like is the objective of this chapter, okay? So the first thing we're going to do is try to find the solutions for the angular rate components in the body fixed reference frame, and that will be in 2.2. Okay, so that's the first thing, and then in the next subsection, we're going to get the solution for the angular momentum vector components in body fixed as function of time, and then we're going to go from body fixed to ECI reference frame to kind of try to understand the three-dimensional rotational motion of a rigid body. And buckle up for that last part. It won't be as trivial as you think it is, okay? But we're going to begin slowly as usual. So in 2.2, we're going to get the solution for the body fixed motion of our angular velocity or angular rate vector. This is the same thing. I'm going to refer to omega vector as angular velocity or angular rate throughout the course, so just make sure that you know that those are synonyms. So body fixed, meaning that we're going to look at the components of this particular vector seen in the body fixed reference frame like that. So again, what we want is to obtain solutions for omega x, omega y, and omega z as a function of time, starting from some random or non-zero initial conditions. Good. So if you go back to what we had for the z-axis, 2.2.1, we're going to first obtain the motion about the axis of symmetry. And if you remember my little 3D drawing of an axisymmetric body, that means that we're going to look at the motion about BZ, because BZ is the axis of symmetry, and that's why we had termed JZ as being JA for the axial principal moment of inertia, okay? About the axis of symmetry or about BZ, this is exactly the same thing. Well, if you go back to what we had for the Z equation in the revisited Euler's equation of motion, we had this very simple expression, which means that the angular acceleration about the BZ direction is going to be 0, which implies that the solution for omega z as function of time is going to be equal to a constant, right? Because the rate of change of constant is indeed equal to 0. Wow, that's it? It's that easy? Yes. As I said, I'm going to begin slowly and step up in complexity as we go through this chapter. But for the motion about the axis of symmetry, we get an angular velocity vector, or a component of the angular velocity vector about this axis, which is constant. Great. But what would be that constant equal to? Turns out that this constant is simply equal to whatever value the motion was initialized with, and that is omega z naught, or omega z at t equals 0. And that's it for the axis of symmetry motion. Good. So now we've solved for one of the three components of the angular rate vector in a body fixed reference frame. And now we can move to 2.2.2. We're going to get the motion this time about the transverse axis. Okay, or in other words, we're seeking expressions for the angular rate components about bx and bx and by. Or in other words, we are seeking omega x function of time equal to whatever, and omega y function of time equal to whatever. This is the objective of this subsection here. All right? Now this one is a bit more complex than the motion about the symmetry axis, because it turns out that the motion about x and y are tightly coupled together. So we'll have to use the Laplace Transform tool, inverse of Laplace Transform, and the good things that you've seen or learned in previous courses. Okay, so if we go back to what we had for the motion about x and y, we had jt omega x dot plus ja minus jt times omega y times omega z equal to 0, because it is a torque-free motion that we are seeking to solve. And here jt omega y dot plus jt minus ja omega x times omega z equals 0. Well, hey, we know better than that now, because we've just solved for the motion for omega z as function of time, and it was determined that omega z as function of time was simply omega z naught as a constant. So we're just substituting the solution for omega z in those two expressions to begin with. Great. And because we are seeking expressions for omega x and omega y as function of time, it means that we're going to solve those two expressions for the derivative of the two variables of interest, and then take the Laplace transform and the inverse Laplace transform to finally get omega x, omega y function of time. Okay? So we're solving these two for the derivative of the variables of interest, and we're going to see that this is equal to I'm going to keep everything on the same side though. So the first step is just to divide everything with jt. So omega x dot plus ja minus jt. All right. Don't want to go ahead of myself. So one step at a time. And this equals 0. And same for the y equation. So omega y dot plus jt minus JA, all this over JT, omega x, omega z not equal to 0. Okay? Now, it turns out that this bunch of terms happens to be a constant, and this is also a constant. This is also a constant, and that is a constant as well, right? Because the actual dynamical variables that will then vary with time in those two equations are the derivative of the angular rates about x and y, and the angular rate about x and y as components here, okay? So to make our life easier, we're going to group those constants together and define one single constant. And specifically, we're going to define the relative spin rate as being equal by definition to JT minus JA over JT, like this, times omega z naught. So our fraction of the initial value we had for omega z is going to be defined as the relative, or referred to as the relative spin rate. Which means that now these two equations could be written in a much more compact way by saying omega x dot minus the relative spin rate, which is altogether a constant, times omega y equals 0. And similarly about the y equations, omega y dot plus the relative spin rate times omega x equal to 0. And hopefully now you clearly realize that those two equations, unlike the equation we had for z, are tightly coupled together because the derivative of omega x is function of omega y, and the derivative of omega y is function of omega x, which means that to get the solution for x and y, we will have to solve simultaneously those two equations of motion. Okay? Good news is that they are so simple that from there we know how to apply the Laplace transform to those two, right? And if you do so, and without forgetting about the initial conditions, because everything we do in this chapter are based on the fact that we have non-zero initial conditions on the motion, such that the body is rotating, otherwise it would be stationary. And the Laplace transform of this, without forgetting the initial conditions, would turn out to be s times omega x in the Laplace domain minus the initial conditions on this variable, then minus the relative spin rate that multiplies omega y, but specifically in the s domain, right? That was in the time domain. Now this becomes in the s domain, and that's why I'm explicitly specifying that the dynamical variables of interest are function of s and not function of time. We're going to do the exact same thing here for the y equation. So derivative of a time variable means that s times the variable, the s domain, minus its initial condition. Now plus relative spin rate times omega x in the s domain equal to 0. Okay? So if you look at that, it means that we have our variables of interest here, 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 and there. So this is what we are going to solve simultaneously, but those are ultimately function of, well, that the relative spin rate, obviously, but also function of the initial conditions, right? So to make my life easier, I'm going to separate those two things. So I'm going to put all the dynamical variables on one side and the initial conditions on the other side of these equations, and then group them in a matrix form and see what we do from there. Okay, I'm going to get S omega x in the S domain minus the relative spin rate times omega y in the S domain equal to the initial conditions applied to omega x. And similarly for the y equation, S omega y in the S domain plus relative spin rate omega x in the S domain equal to the initial conditions given to omega y at t equals 0. Good. The next step, as I said, is a matter of rearranging those two equations in a matrix form because they need to be solved simultaneously. So playing with matrices is going to be a handy tool to solve those two equations at the same time. Okay. So I'm going to group the S variables and the relative spin rate variables in the matrix times the dynamical variables here equal to the initial conditions on the other side. Right, so a 2 by 2 that will multiply omega x in the S domain, omega y in the S domain equal to a 2 by 1 with constant numbers representing the initial conditions on omega x and omega y. So if I want things to look like that, it means that here within this matrix I need to have S. I'm just translating that equation first in terms of matrix. So S omega x minus relative spin rate times omega y equal omega x naught. That works out. And similarly here, I'm going to get S. Oh, sorry, the S is for the omega y. So S times omega y plus relative spin rate times omega x gives me omega y naught. Cool. This is what I'm trying to solve for. First in the S domain and then applying the inverse Laplace transform to get the solution in the time domain and finally obtain an analytical expression for both omega x function of time and omega y function of time. So to solve that in the Laplace domain, all I need to do is take the inverse of this matrix. So meaning that we're going to get then omega x here, omega y in the S domain equal to the inverse on that side as well. So S minus relative spin rate S, inverse of this, times the initial conditions on both x and y angular velocity components seen in the body fixed reference frame. Oh boy, the inverse of that. Okay, not that big of a deal. Just need to remember how to do the inverse of a 2 by 2 matrix, and thank God it's not the inverse of a 3 by 3 matrix, which again you shouldn't have to do at any time in this course. That would be typically applied to rotation matrices, but you know that the inverse of a rotation matrix is equal to its transpose. Okay, so if you have a random matrix A, I'm going to denote with A11, A12, A21, A22. We know that the inverse of that is going to be equal to 1 over the determinant of this matrix A times 2 by 2, where those two terms are flipped around, A22, A11, and those two other terms are simply multiplied with minus 1, minus A21. And the determinant of this matrix is going to be this times that minus this times this. So A22 times A11 minus A12 times A21 times this 2 by 2 matrix obtained from the original one. 2, 1, 1, like that. Okay? So let's apply this principle to what we have to play with here. I'm going to do that on top. So for omega x, omega y, always in the S domain, we're going to get inverse of this. So 1 over the determinant, which is going to be S squared minus this times this, so plus relative spin rate squared. That is 1 over my determinant times the 2 by 2 that I'm going to construct out of this original 2 by 2. And this is going to get multiplied with my initial conditions like this. So this 2 by 2 matrix, I'm just taking those two terms, flipping them around. It's going to be exactly the same. So S. I'm going to multiply those two by -1, which would turn them to be spin rate and negative of the relative spin rate there. Okay. The next step is to multiply what I have inside my matrix with this factor. Okay. So again, this is omega x, omega y in the S domain equal to the 2 by 2 times the 2 by 1 with constant initial conditions here. This 2 by 2 will be 4 fractions. S, relative spin rate minus relative spin rate and S. And the denominator will be for all these terms the same, which is S squared plus relative spin rate squared. Just like that. Okay, and this is where we need to invoke the Laplace transform. Assuming that you've heard about Laplace transforms and inverse Laplace transforms in the past, which hopefully is a good assumption. Otherwise, just do as I say from there on. Okay? So if you have the Laplace transform of cos of omega t, this will turn to be in the Laplace domain equal to S over S squared plus omega squared. And similarly, if you were to take the Laplace transform of sine omega t in the time domain, that would give you in the S domain omega over S squared plus omega squared. Turns out this is pretty much what we have inside this 2 by 2 matrix, right? Where the generic omega used in Laplace transform tables happens to be our relative spin rate, capital omega here, okay? And those two things mean that taking the inverse Laplace transform then of S over S squared plus omega squared would give back cos of omega t. And taking the inverse Laplace transform of this would give you the sine omega t. Okay, so inverse Laplace of omega over S plus omega squared would give you sine of omega t back in the time domain. And again, those things can be found in mathematical textbook like the CRC mathematical recipes or something like that used to be called. It's a big textbook, bigger than the Bible actually, and you have like pages and pages of Laplace transforms of some generic trig functions and whatnot, and the inverse Laplace transforms as well. So I don't assume that you need to know that on top of your head. We're just using those two specific ones because this is what we actually have inside this matrix, okay? So there, I am then applying the Laplace transform over this matrix equation, which would then give me omega x, omega t as function of time, and I am omitting the time dependency for conciseness, okay? Whenever we're in the S domain, I was explicitly written function of S, but I'm not going to do that for function of time because otherwise I'll keep writing for forever, okay? So omega x, omega y equal to a Laplace transform of this. So S over S squared plus a constant square gives me cos of that constant times t. Now, inverse Laplace of a constant over S squared plus a constant square is that one. And that gives me sine of the constant, which happens to be relative spin rate in our case, times time. And doing exactly the same thing for those two things will give me minus sine omega t and cos omega t. And let's not forget about our initial conditions to make sure that the rigid body is undergoing a rotational motion. Otherwise, under the torque-free assumption, if all initial conditions had been set to 0, well, the rigid body would be inertially fixed, it wouldn't be rotating at all. And the solution for omega x, omega y, omega z as function of time would be quite boring. That would just be equal to 0. But here we want to spice things up a little bit by assuming that those initial conditions are different than 0, obviously. Okay? Good. So now I'm going to rewrite those two equations in terms of two separate equations instead of keeping them in a matrix form. We don't need to use matrices anymore for the process. So omega x as function of time is going to be equal to cos nt. That's not n. It's just capital omega. Wow. Cos relative spin rate times time, that multiplies omega x naught plus sine omega t, that multiplies omega y naught. And for omega y as function of time, we're going to get minus omega x naught, that multiplies sine omega t. And then plus omega y naught, which multiplies cos of the relative spin rate times time this time around. And that would be a valid solution for omega x, omega y as function of time. Right? These are analytical expressions that are time explicit. So if you want to know the value for omega x, omega y at t equal 100 seconds, based on the fact that the motion was initialized with specific values for omega x, omega y naught, then you just get your answer from that. And that depends on the relative spin rate, which is self as function of the actual principal moment of inertia, the transverse one, and omega z naught, if you remember from before. So based on all those quantities, which you know at t equals 0, you can then calculate omega x, omega y at any point in time. And that could be the end of the day, and that would be done. But in terms of understanding really how is the angular velocity vector spinning in 3D space with respect to the body fixed reference frame, we are going to keep playing with those equations until we find something that we can wrap our head around. Okay? And specifically at that point, we're going to make use of the transverse angular velocity. Transverse angular velocity, which happens to be omega t equal to square root of omega x squared plus omega y squared. And similarly, the transverse angular velocity is going to be equal by definition to square root of omega x naught square plus omega y naught square, like that. Okay? So for that reason, because of this fact, we're going to take our equations here and divide and multiply the right-hand sides of those two equations by this. Okay? And specifically with that first, and then we're going to replace what we have left with maybe omega t naught or omega t. We'll see what happens to the equations. And the reason why we are invoking this new variable in the process is that with omega t, it's going to be a lot easier to understand the three-dimensional motion of the angular velocity vector seen from the body fixed reference frame's perspective. Okay? So here we go. Taking those two equations and simply multiplying and dividing the right-hand sides with this factor. So, square root of omega x naught square plus omega y naught square times omega x naught over the same thing over square root of omega x naught square plus omega y naught square. This was multiplying cos of our relative spin rate time plus omega y naught over the same denominator. So that's our square root of omega x naught square plus omega y naught square. And this was multiplying sine of omega t. Okay? And we're going to apply the same treatment to the y equation. So times this factor to the right-hand side, and then divided by the same factor. And here I'm just going to rearrange the order to begin with the positive number here, just because. There's no good reason for it. So omega y naught over the square root term times cos of omega t plus, or minus rather this time around. So minus omega x naught over the same denominator as before times sine capital omega t. And let's not forget to close the bracket after all of this. Okay? So, now we'll have to go back to the definition of the transverse angular velocity at t equals 0 and make use of this fact, such that we could replace those last two equations that are quite lengthy in this form with a more compact expression. So this is the transverse angular velocity at t equals 0, and same for this, and same for all the square root terms. So then I'm going to say that omega x is going to be the transverse angular velocity component at t equals 0 times omega x naught over omega t naught cos omega t plus omega y naught over omega t naught sine omega t, close the bracket. And here, same idea. We have seen just before that that was actually omega t naught. So this could be omega t naught times omega y naught over omega t naught, the transverse initial angular velocity, times cos of omega t, minus omega x naught over omega t naught times sine of omega t, and close the brackets. All right. So this is a lot nicer than that, and the only reason we keep going with the equations, although we already had obtained analytical expressions for omega x and omega y function of time previously, is because we are trying to picture the singular velocity vector moving in 3D space in the body fixed reference frame. And again, the use of the transverse angular velocity concept is going to be of a great help for that specific purpose. Okay? Such that let's keep simplifying things a little bit here, and that was just for omega x, by the way, omega x, omega y. We're going to define omega t naught as function of omega y naught and omega x naught in terms of geometry. So if you were to look like a bird's eye view of the body fixed reference frame with BZ coming out of the board towards you, it means that omega x naught in terms of magnitude will be along this direction. This is bx and by, and that would mean that omega y naught would be along this direction as well. Omega y naught. And by virtue of the definition of omega t naught, and if you remember, we had said that omega t naught was equal to the square root of the x square plus the y square of omega, that means that this is actually equal to this, okay, in terms of geometry. And to further simplify the process of deriving equation, we're going to define the angle between omega y naught and omega t naught here as phi, okay? Not to be confused with the roll angle we saw in chapter 1, nothing to do with it. This is just some random angle between omega y naught and omega t naught here, such that we can say that sine of this angle is going to be equal to this side, so omega x naught over omega t naught. And similarly, we could derive cos of this angle, which would be equal to omega y naught over omega t naught. That's kind of useful for us because if you look at what we have in those two relationships for omega x, omega y, this is exactly what we happen to have, right? We always have the ratios of omega x naught over omega t naught and the ratio of omega y naught over omega t naught. So we're going to replace those two with those trig functions and simply rewrite that omega x is going to be equal to the initial transverse angular velocity that multiplies x over t is your sine phi, and cos of the relative spin rate time plus the omega y naught over omega t naught is cos of the angle here, so cos phi times sine omega t. And let me erase the stuff in red, just like that, so I can actually close this parenthesis here and do the same thing for the y equation. So omega y is going to be equal to omega t naught. The y over t was your cos, so cos phi cos relative spin rate time minus the omega x over omega t was your sine of the new angle phi, then sine omega t, just like that. Cos cos, sine sine, sine cos, cosine, plus minus. We're good, we're good. But we're not done yet. Okay, we're going to keep working on those two expressions until we get to something really nice and neat that we can all easily understand. And the trick here is to make use of some trig identities, and specifically that cos A, cos B, and minus sine A, sine B is equal to cos of A plus B, and similarly that sine A cos B plus cos A sine B is going to be equal to sine of A plus B, just like that. Because, surprise, surprise, this is exactly what we have here. It's like magic, I'm telling you. Okay, so sine cos plus cos sine. Sine cos plus cos sine, meaning that I could write omega x simply as omega t naught that multiplies sine of phi plus omega t, like that. And the same for omega y. I'm going to say that this is the initial transverse angular velocity. And now we have cos cos minus sine sine. Cos cos minus sine sine. This is cos of the two angles added together, right? Because a relative spin rate here, capital omega, is in radians per second times time. That gives us an angle. And this angle is directly in radians, so that works out in the trig functions here. And you can see that this is kind of getting down to something very basic at the end of the day, okay? What now? Okay. All right, let's keep going a little bit further. And let's make use of the fact here that omega x squared plus omega y squared is actually equal to the transverse angular velocity squared from the previous definition of the transverse velocity. Okay? So if I have my omega x here, my omega y here, I could square them both and add them together. Okay? Which is going to mean well, that works out in terms of the analytical expression for x and y as function of time, but the next few steps are there to discover a very, very important result of this derivation, and that is that, again, squaring those two equations and adding them together would give me omega t naught squared sine square of two angles added together plus omega t naught squared cos square of the same two angles added together, and that was for omega x squared plus omega y squared obtained from these two relationships. And by virtue of this, we can say that all of that is actually equal to omega t squared. Okay? So what do we see? Well, we can factor out the omega t squared term and just write sine square of an angle, because altogether this happens to be an angle, plus cos square of another angle is actually giving me omega t squared. Ha! Look at that. All this is 1. Yay! Which means that omega t naught squared is equal to omega t squared. Or that omega t as a function of time is going to be equal to a constant, and that constant is equal to the initial value given in terms of the angular velocity vectors along x and y combined together to give me my transverse angular velocity as a function of time. And let me highlight that in red because of the importance of that key result we've just obtained. Okay. So now what we're going to do in the next section, now that we've derived all the tools we needed to assemble those tools or those building blocks together to figure out the three-dimensional motion of the angular velocity vector. What was I about to say? We've just derived all the blocks to analyze the three-dimensional motion of the angular velocity vector, which now we're going to do in the next subsection, which is going to be 2.2.3, 3D motion of what? Well, we are still within 2.2, which was body fixed motion of angular velocity vectors. So that refers to 3D motion of our angular velocity vector in body fixed reference frame. Okay, so these were the two key things we've obtained in 2.2.2. Let's not forget about them because we're going to make use of them in what's coming up next here. Okay, so based on everything we did here, it means that the norm of my angular velocity vector, simply denoted by omega, can also be obtained from the Euclidean norm of omega seen in body fixed reference frame, or in other words, by squaring its x component plus its y component and its z component, like that square. But we know from this, which was actually coming from even earlier, that omega is actually the square root of omega t squared plus omega z squared. Whoa. Wait a second. Are you kidding me? No, I'm not, right? You see what I'm seeing here. This holds valid. But hey, we've just established from before, from 2.2.2, that this was a constant. And a constant actually equal to its initial value, omega t naught. But from 2.2.1, we had also established that omega z was another constant equal to its initial value, omega z naught. Whoa, this is mind-blowing, isn't it? Because that means that we can now say that the norm of the angular velocity vector shall remain constant whenever there's no torque applied to the body and that the body is just spinning with its angular or its initial conditions. Okay? Wow. This is fantastic. What a great discovery we've just made in 2.2.3. Okay. But although the norm of this vector altogether is constant, and although the z component is constant, it doesn't mean that the x and y components are also constant. because we had obtained expressions for them as function of time. Okay? So what we're going to do next is to define yet another angle denoted by mu. And we're going to say that mu is actually what we had inside the trig functions previously, and that was omega t plus alpha. Remember that? Such that if you go back to the analytical expressions we had obtained in 2.2.2 for omega x and omega y, making use of this new angle means that we're going to write omega x equal to omega t, or omega t naught, doesn't matter, it's the same thing, right? So omega t times sine of mu, omega y equal omega t cos of mu. And for completeness, I'm going to complete the entire set of components for the motion of omega in the body fixed reference frame. I'm going to just report here what we had found previously, and that is that omega z is equal to omega z naught. And that is the solution we were after. Or in other words, how to analytically describe the time history of omega x, omega y, and omega z. Or in other words, what would be the three-dimensional motion of this angular velocity vector in terms of its x, y, z components seen from the body fixed principal axis reference frame of our axisymmetric spacecraft. But now we have all the tools to really picture this in 3 dimensions. Okay? Now, let me draw a body fixed reference frame with Bx out of the board towards you, By over here, and Bz over there. Now, obviously, our spacecraft, characterized by its body fixed reference frame, right, this is all at the center of mass of our rigid body, is moving in 3D space. So with respect to some inertial reference frame, that body fixed reference frame is tumbling around about all 3 axes simultaneously based on its initial conditions and based on the geometry of the spacecraft, or in other words, based on the principal moments of inertia. That I do acknowledge. But here, that's not exactly what we're looking at, because what we're actually looking at here is just the motion of the angular velocity vector seen from that perspective. So I am sitting on a spacecraft. So to me, that spacecraft isn't moving with respect to me because I'm sitting on it. But I'm just looking at the motion of the angular velocity vector spinning with respect to myself, which I think of myself as being fixed because I am sitting on a body fixed reference frame. So this is what we are looking into here, because those expressions are the expressions for x, y, z components as function of time of the angular velocity vector, but seen in terms of the body fixed reference frame. So don't get confused. This is a body fixed reference frame point of view of what would the motion of the angular velocity vector look like. So what do we know? Well, we know that the norm of my angular velocity vector shall remain constant at any time. So this is angular velocity vector. It means that this vector will not shrink or expand as function of time, and the reason for that is because there is no torque applied to the rigid body, right? Torque-free attitude motion. Furthermore, we know that the projection of this vector onto the x, y plane, which happens to be our transverse angular velocity, omega t, is also constant in magnitude. Okay? So the norm of this projection is constant. The z projection of omega is constant, yet omega x and omega y aren't constant. So at one point, it means that as this vector swings in 3D, we could get omega t completely aligned with bx, and therefore at that point omega y would be equal to 0. At some other time of the future, we could have this vector omega t still keeping the same magnitude, yet oriented directly along dy, which would mean that at that point omega x would be equal to 0. So we could see that although that the length of this is constant, and that the length of this is constant, as this vector moves in 3D space, the x and y components will not be constant. And in fact, just by looking at those expressions, we are able to say that the x and y components, or the projection of my angular velocity vector onto this plane, which happens to be omega t, will draw a circle onto this plane, which implies that this vector swings and rotates about bz like that its projection will draw a circle. Or in other words, that this vector, which is omega, will follow a circular path around bz. And this way, the projection here will also draw a circle in 3D space, which I'm not attempting to draw here. We'll just mess things up, I think. Should I try? No, it's going to look awful. I'm going to leave it like that, okay? And the angle we've just defined is function of time, right? Because if you remember, that was the angle here between omega t and omega y, or in other words, this. But this angle is not always equal to the same value. In other words, the angle between by and omega t is not always constant, because yes, initially there is an offset equal to phi, but as time increases, this contribution starts playing a role. So this angle is actually equal to mu here, okay? Such that the rate at which the angular velocity vector swings around bz, or draws a circular path around bz, will be at a rate equal to mu dot. And that rate is actually equivalent to the relative spin rate, which is equal from way before to the transverse principal moment of inertia minus the actual one over the transverse, and all this multiplied with the initial kick we gave to the z component of our angular velocity vector, or in other words, the initial value imposed on omega z. Okay? That's what it is. So this is the three-dimensional interpretation of the equations we derived for omega x, omega y, omega z function of time. And this told us that, again, the motion of the angular velocity vector seen from that body fixed perspective, not seen from the inertial perspective, completely different, okay? But seen from the body fixed reference frame's perspective, draws a cone about bz, essentially, right? Does that look like a cone to me? Or the tip of this vector draws a circle, and hence the projection of this vector onto bx, by will draw another circle, a flat circle around bz, and that vector here rotates at a rate of mu dot equivalent to the relative spin rate, like that. So let me write it in words. So we've established that omega vector rotates about bz at a rate equal to the relative spin rate. So just depending on the shear geometry of your spacecraft, quantified through the transverse and the axial principal moments of inertia, or the mass distribution of the spacecraft, and the initial component of the omega vector along BZ, we're going to get a swinging motion of the angular velocity vector like that around BZ. Okay? That rate is constant, obviously, because that was a constant, and those three things are constants, unless all of a sudden the mass distribution within the spacecraft would happen to change. So if you were to deploy the solar panel, all of a sudden those quantities would drastically change, and that would change the rate at which all of a sudden the angular velocity vector would rotate about BZ like that. The last thing is that we're going to define an angle between BZ and that angular velocity vector denoted by beta. Okay? Great. And that angle is obviously constant throughout the circular motion of the tip of the angular velocity vector. So I'm going to say omega rotates about BZ at a rate of this, and with beta equal to a constant. Isn't that beautiful? We went from Euler's equations of motion, took some simplifying assumptions on the geometry of the spacecraft and on the environment in which the spacecraft is spinning in, i.e. the torque-free assumption. And then we just derived the equations. We applied the Laplace Transform, the inverse Laplace Transform, and ended up with what we were seeking, and that is analytical expressions for x, y, z components of this angular velocity vector inside the body fixed reference frame. Okay. Now this does not inform us about the way the body fixed reference frame itself rotates in inertial space. That will come next in 2.4 probably. Yeah, inertial attitude motion, and that'll be the most complex thing we're going to look at in this entire chapter. So I think we have time for this lecture to complete 2.3. Now that we've established the body fixed motion of the angular velocity vector, we're going to do the exact same thing, but for the angular momentum vector, okay, in 2.3. This section is going to be a little bit more fast or quick than the angular velocity vector because of what we've already established. We want to make use of the results obtained in 2.2. Okay? So I don't need that conclusion anymore because you wrote it on your piece of paper. Which, by the way, I highly encourage you to take a loose stack of loose sheet of paper whenever you watch those lectures, and make sure you scribble all equations and all figures I'm drawing and writing on the board, instead of just passively looking at what I do on the board and the printed lecture notes. So by writing everything I do on the board yourself, you are actively learning as you watch the lectures. In this way, all the information, because you watch and write, is going to be a lot more imprinted in your brain, okay? So this is really active learning as opposed to passive learning. We're just watching a video while drinking tea or watching a YouTube video or talking to your girlfriend or something like that, okay? So be active in the learning process. Write down everything I write, and after watching an online video, just go back to the printed lecture notes and then do a comparison between your notes and my notes, and this way you could fill the blank and draw all the missing figures in the notes, okay? Just a tip to do well in this course. But that was the exact same thing for orbital mechanics. So obviously by now you should be familiar with my way of teaching, okay? So 2.3. body fixed motion of angular momentum vector. Quite a title for a subsection. Okay, so let's first start from the beginning, and let's say that the angular momentum vector, represented by h, obviously can be expressed in terms of its components in the body fixed reference frame like that. Same old, same old. And furthermore, we're going to define those three components in the body fixed reference frame simply as hx, hy, and hz, just for simplicity's sake. So here the objective would be to obtain the solution for hx, hy, hz as function of time, exactly as we did for the angular velocity vector in the body fixed reference frame. Okay. So if you remember what we did at the very end of chapter 1, which was a derivation of Euler's equation of motion, we had said that the angular momentum is equal to the inertial matrix times the angular velocity. So here we're not going to redesign the wheel, because we know that h being equal to j omega allows us to write hx, hy, and hz equal to jx omega x and jy omega y and jz omega z. But remember that here we are not dealing with x, y, z in terms of principal moments of inertia by virtue of our axisymmetric rigid body. So those two things were replaced with jt, our transverse moment of inertia, so respectively times omega x, omega y, and jz had been replaced with the axial principal moments of inertia, denoted by ja, omega z. All right, well, that's easy because we had obtained initial solutions for these things. So let's just plug them back. jt times, that was omega t sine mu. This is jt omega t cos mu. And this is ja omega z. And omega z is a constant and equal to omega naught. Okay? So, what can we say about that? Well, the first thing is that we could look at the z equation and realize that, well, because omega z was a constant and equal to its initial value, this constant times ja, which is a constant, implies that hz is similarly to omega z a constant. Or in other words, both omega and h vectors aren't increasing their z magnitude as time goes by, right? And turns out that similarly to omega, we're going to get hx and hy that will vary with time, but not hz. All right? What we're going to do next is use the same trick that we've employed for the angular velocity, and specifically the transverse angular velocity definition we had in place. So here we're going to define the transverse angular momentum as being the square root of the x component square plus the y component square, like that. Okay? Such that we could use these and rewrite ht as being equal to jt omega t sine mu square plus jt omega t square cos mu square, and then square root of all that. And obviously what I can do here is factor out jt omega t out of everything and be left with the square root of sine square mu plus cos square mu, which turns out to be 1. And therefore, surprise, surprise, ht is simply equal to jt omega t. Omega t from before was a constant and equal to omega t naught. And therefore, because jt is another constant, it implies, let me just report ht here, that ht altogether shall be another constant. Very similar to the conclusions we had drawn from the angular velocity analysis, because we had the z component of angular velocity being constant. And turns out that the z component of the angular momentum vector is also a constant. We had also discovered in the previous section that omega t was constant. And turns out then that ht is constant too. So those two things are very similar to each other. Okay? So based on those things and based on those equations here, we now have all the building blocks to look at the three-dimensional motion of the angular momentum vector seen in the body fixed reference frame. And that'll be 2.3.1. So you see that by virtue of all the derivations we did in the previous section, that one is a lot quicker to analyze because we are reusing the previous results based on the fact that h is simply j times omega. And we know everything we needed to know about omega, so we're just scaling things by a factor of jt and or ja in that case, okay? So 3D motion. 3D motion of what? Well, 2.3.1 is under angular momentum vector, the body fixed reference frame, so that would be 3D motion of angular momentum vector in terms of components. Now, what can we say about the norm of this vector, which is going to be denoted by h and calculated by taking the Euclidean norm of the components of h in the body fixed reference frame, or in other words, taking the square root of hx squared plus hy squared plus hz squared. I'm going to do exactly what we did for the angular velocity vector analysis in 2 dimensions. To then rewrite that in terms of the transverse angular momentum. So we're seeing that h is going to be equal to square root of this is transverse angular momentum square and plus hz squared. Wow. That we couldn't expect, right? This is mind-blowing again because we know that hz is a constant and equal to hz naught. And we've just determined right now that ht naught, or ht was a constant equal to ht naught. So therefore, altogether, wow, h is going to be equal to a constant. So the norm of our angular velocity vector will remain constant. Okay? Same as what we had for angular velocity, where the norm of the angular velocity vector was constant. Although it was moving, that vector was not shrinking or expanding with time. And we have the exact same thing for angular momentum. Okay? But don't fall into the trap of saying because this is constant and because those two things are indeed constant too, it means that h is not moving. Well, no. That is constant, that is true. But hx and hy are not constant by virtue of the equations we had just derived previously. But although they are moving in a way that makes ht, so the combination of those two, to be constant and equal to ht naught. So altogether, making use of the ht notation, we could rewrite the time explicit analytical expression for hx, hy, and hz, and make that equal to ht times sine mu, ht cos mu, and here hz naught, which is constant, or in other words, ja omega z naught, which is constant, obviously. Okay, so this is the analytical expressions that allow you to calculate hx, hy, and hz at any point in time, because time is part of mu, right? Because mu was relative spin rate times time plus the initial offset between the by unit vector and, in that case, the transverse of the angular momentum. So let's have a look at what it looks like in 3 dimensions. Okay, so let me draw a big body fixed reference frame as I did before, with bx normal to the whiteboard, by to my right, and bz going up inside the whiteboard plane. Okay, well, we know the first thing is that h, vector in terms of its length, remains constant throughout time. We know that the projection of h on the bx by plane, well, the length of that projection will remain constant, and that projection happens to be our transverse angular momentum vector ht. Does that look familiar? Hopefully it does, because this is the exact same thing as what we had before, where the angle between dy and the projection of the vector onto bx by happens to be mu. Okay, and if you look at the equations here, it means that the transverse components x and y together, because this is sine and because this is cos, it means that this vector draws a circle around bz, which implies that this vector also, or the tip of this vector, has to draw a circle around bz too, because that one is just the projection of h, which means that the h vector draws a cone about bz at a rate equal to mu dot, where again mu dot is the same as the relative spin rate. Okay. The only difference is that the angle that the angular momentum vector makes with respect to bz is different than before. So this time I'm going to denote this angle as gamma. Okay, before it was beta. Was it beta? Yeah, before it was beta, now it is gamma. Turns out that gamma has a special name and is known as the nutation angle. Okay, so let me summarize the motion of the angular momentum vector seen from the body fixed reference frame, which is located at the center of mass of our spacecraft, like that. So we're going to say that h rotates about bz, or around bz, along a circle, please, thank you, at a constant rate equal to mu dot equal to the relative spin rate. Okay. and with an angle equal to the notation angle with respect to BZ. So this angle here is actually defining the opening of that cone. The larger the angle, the larger the opening of that cone. And the way this angle is defined is just through the initial conditions imposed on the hx, hy, and hz direction. Because for a given h vector, if hz would be less, that would mean that your h vector would look something like this, and therefore the opening of the cone would be much larger. For a larger hz component, it means that this h vector will look something like that, and now the cone is closing and drawing a smaller circle or tighter circle around BZ. In the next section, which is all about then from the body fixed motion of those two vectors, how can we infer the ECI motion of the body fixed reference frame? And that will be the most challenging aspect of this chapter. We're going to make use of the fact that we can draw some relationships just from sheer geometry of the problem. And if you were to look at h vector, like that, inclined with respect to by and bx, and if you take its projection along dy and bx plane, okay? If that is your nutation angle, that means that here, between h and ht in terms of magnitude, you would also have the nutation angle here, and therefore you'll be able to say that sine of the nutation angle is going to be equal to ht over h. And similarly, cos of the nutation angle will be equal to hz, or this side, which is along bz, so hz over h. Just two useful relations to keep in your back pocket for what will be coming up next. And that one is dead in the next lecture. Okay? So, to kind of sum up what we did today, the first thing was to describe the problem at hand. Axisymmetric spacecraft, no torque applied to the spacecraft. So in other words, how could we investigate the natural motion of the spacecraft in space? That assumption of torque free again is valid for a short period of time because the actual attitude perturbations or the perturbing torques applied to the spacecraft are low frequency torques and are low in magnitude. Okay, so over one orbit, the effects will be felt quite a bit by the spacecraft, but over a short period of time, the torque-free assumption kind of makes sense. Based on the axisymmetric geometry assumption and the torque-free assumption, then we went back to our earlier equations derived for a principal axis reference frame and revisited those equations by plugging in those two assumptions. And then we had discovered right from the bat that omega z was equal to a constant and equal to its initial value. Keeping in mind that the initial values here are crucial for the entire analysis, because if there's no torque applied to the body, and we consider that at t equals 0, the components of the angular velocity vector are all equal to 0, and that would just mean that the spacecraft would remain stationary. But if the spacecraft had some initial velocity components, omega x naught, omega y naught, omega z naught, the spacecraft would keep spinning in some ways. So the objective was to determine, first, what would be the motion of our angular velocity vector as seen from the body fixed reference frame perspective. And we've established that the angular velocity vector was spinning about the BZ unit vector attached to the rigid body itself or attached to the spacecraft. By doing a similar analysis for the angular momentum vector, we've discovered that also the angular momentum vector was moving about BZ. Okay? And that those two vectors are moving at a constant rate. The only difference is the angle that those two vectors make with respect to BZ and their respective magnitude. Those two things are different between angular velocity and angular momentum vectors. Still, their motion is exactly the same. They both draw a cone about BZ at a rate equal to their relative spin rate, which is itself calculated based on the geometry of the rigid body, GA and GT, and also the initial components along the z-axis for the angular velocity. Okay? So that's the bulk of the work we did today. And next up, we're going to dive into the most challenging aspect of this chapter, which has a heads up. You may not be able to wrap your head completely around the resulting result we're going to get. About the result we're going to get, because figuring a rotational motion of a rigid body in 3D space is very, very challenging. Yet that would give you the initial idea. And the more you're going to come back to the lectures and the more you're going to come back to the notes and maybe watch some additional videos on the web or picking up a textbook, then you will start to understand, now I know what the 3D motion of the body fixed reference frame with respect to ECI will look like. Okay, but that'll be for next time. Until then, as usual, keep up the good work. I'll see you soon. Goodbye.